So now we're ready to do trigonometry on the unit circle. So we're going to draw the Cartesian plane like this and a unit circle. Okay. So this is 1 here. This is, well, actually it would be 1, 0. This would be 0, 1. Okay. And imagine I have maybe an angle, theta, like that. This is theta. Okay. This is the point where this line intersects the unit circle. So we're going to say that the coordinates are x and y. Okay. Now the equation of a circle is such that the coordinates satisfy the Pythagorean identity. Why is that? Well, look at this triangle here. Okay. The one in red. Notice that this side here, this is x, this is y. I could have, like, so very, very quickly, I could have also, you know, an angle like this, okay? Now the triangle I'd look at is this one here, okay? And if this is x and y, now x would be negative, a negative number here. So this side here would be the absolute value of x. This side here would be the absolute value of y. So this is what's true in general. So the sides are the absolute value of y and x. But since we're on a right triangle, right? If we square that and square this, we're gonna get the radius. But the radius here is this radius here is 1, right? Because it's a unit circle. So this is what unit stands for. Yeah, a radius of 1. So radius of 1. So this is going to be 1 squared. Now if you square something that's an absolute value, it's just like squaring a number itself. Like, for example, if you've got -1 and you square it, it's just like squaring 1, because it's going to give you 1 in the end. If you square -2, you're going to get 4, which is the same as squaring 2. So we can sort of ignore the absolute values when we square it. So we could just write x squared plus y squared equals 1. So, and you'll recognize here the equation of the circle. So this is how the equation of the circle is obtained. It's just the Pythagorean theorem. Okay, so I'm just going to erase this now. Okay, so this was just to explain that x squared plus y squared, no matter where they are in the circle, there's the sum of the squares of the coordinates is going to be equal to the radius square, which is 1 in this case. Okay, now I'm going to construct another triangle that's going to be similar to the blue triangle, to the red triangle. So it's going to be in blue, and I will just extend that side here, the radius. I will extend it. Okay, so this line here, or this side here, okay, is, okay, if I'd extend it, it would just touch the circle at 1, 0. So we'd say it's tangent to the circle. Okay, so we could say that the segment is tangent to the circle. Okay, we're going to call that segment the tangent. We will name it, or call it, or I should say name it is better. We'll name it tangent. So that's, when we're going to refer to tangent, it refers to that side here. This other side here, okay, the hypotenuse of this triangle, it cuts the circle, right, at xy. Okay, in geometry, when something cuts or intersects another curve, we say that this curve is or a line is a secant. So here, segment cuts through the circle. Okay, we name it secant. So there's now secant and tangent. What about sine and cosine? Okay, let's take a closer look. So let's come back to our circle in red. I'm going to use a red pen just to emphasize this. So what's the cosine of theta? Cosine is adjacent over hypotenuse, right? So let's look at the red triangle. So the adjacent side to theta is x. The hypotenuse is the radius. It's 1. So actually x is cosine. So this guy here, this side here, this is cosine on our picture. What is sine? Well, sine of theta will be opposite over hypotenuse. This is y over 1. So y is the sine. And tangent, and now you're going to say, well, tangent, like this is weird. Like there's tangent here, there's tangent there. Like, we have two tangents. We'll see that actually no. Tangent, according to our previous video, this is opposite over adjacent, right? Now opposite is y over x, okay? But say take a closer look at the blue triangle. Okay, let's say this is origin. Let's say this is point A, and this is point B here. So the OAB are the vertices of the blue triangle. If I look at the blue triangle and the red triangle, those are similar triangles. So the ratios of corresponding sides are equal. So the opposite side to theta on the blue triangle is AB. And the opposite and the adjacent side of the blue triangle for angle theta is OA. Okay, so AB is actually what I've called the tangent. And OA is actually the radius of the unit circle. That's actually 1. So you can actually see that tangent of theta is really what I've called the tangent on the picture. So it's kind of a cool thing to see here. The blue triangle sort of illustrates geometrically that this height here of the blue triangle, physically it corresponds to the tangent when we write it as opposite over adjacent for the red triangle. So so on the red triangle we have that the two sides that are corresponding to x and y, those are cosine and sine. And for tangent, you have to move to the blue triangle, and the height of that triangle is the tangent. Now, one more thing to notice is also because of tangent, which is y over x. Now we just saw that cosine is x, sine is y. Right? So we could just replace y and x by sine and cosine. And if we do this, this is going to be sine of theta over cosine of theta. Okay. Now finally, one last thing is if I look at secant, so secant I've just mentioned that it would be the hypotenuse of the blue triangle. It's the line that cuts through the circle. But let's also compare the red triangle and the blue triangle to establish a relationship between secant and sine and cosine, just like we did for tangent. So if we look at secant, so secant, okay, and we'll actually call it secant of theta, just like we have tangent is like tangent of the angle theta. So secant of theta, which is the hypotenuse of the blue triangle, over, let's say, OA, okay, which is actually going to be 1. Okay, that's like the base of our blue triangle. Okay, that's in the same ratio as the hypotenuse of the red triangle. Maybe I'll just keep it in blue. Okay, over the base of the red triangle, which is x, right? Okay, and x will turn out to be cosine as before. So secant of theta, okay, over 1, because OA is 1, is 1 over, and x turns out to be cosine. So essentially, dividing by 1 doesn't do anything. So secant is going to be equal to 1 over cosine. Okay, so to summarize all this, okay, unit circle, okay, if I have an angle here, okay, there's this triangle, but there's also this one, okay, this side, that's tangent theta, this side, that's secant, secant of theta. Now secant of theta, we would just abbreviate it to sec. Okay, sec theta. Okay, this is cos of theta. This is sine of theta. And tangent is equivalent to sine over cosine, while secant is 1 over cosine. Furthermore, if this point has coordinates xy, well, xy corresponds to cosine and sine of theta. Now, there's another angle that's interesting on this diagram. It's this one here. Okay, this is the complementary angle of theta. So this is pi over 2 minus theta right there. Okay, so we're going to swap now the angles theta and its complementary angle. So if we swap the non-right angles of the triangle, we obtain the following figure. Figure is as follows. Okay, so you've got again your unit circle. Okay, but now theta is here, and this is pi over 2 minus theta. Okay, and maybe I'll extend once again this triangle, get a similar triangle, like, well, not my best triangle, okay, like this. Okay, so now we're and maybe I'll erase this. We can't see anything, yeah, can we? So this here, this is pi over 2 minus theta. Okay, now this complementary angle has a secant and a tangent, but because it's a complementary angle, we're going to call those values the cosecant and the cotangent. So the secant of the complementary angle is the cosecant, and we're going to write it as cosec. Okay, and that's going to be the cosecant of theta. So the secant of the complementary is the it's called the cosecant of theta. Okay, and similarly, so we're going to write it as cosec theta. The tangent of the complementary angle is the cotangent of theta, and we're going to write it cotan theta. So let's see in terms of sine and cosine what those quantities are. Okay. So this side here, this is what we're going to call, this is the secant of the complementary angle, but it's going to be called the cosecant of theta. While this side here, which is the tangent of the complementary angle, is going to be called the cotangent of theta. Now by, maybe I'll add here, this point here, we've swapped the angles. By swapping the angles, okay, we're also going to swap the, so we're going to swap the coordinates. So by swapping the angles, essentially we're reflecting this point across the line y equals x. So it's going to swap the coordinates. So instead of having sine and cosine of theta, no, sorry, the other way around. Instead of having cosine and sine, we're going to have sine of theta and cosine of theta here, because the values of x and y have been swapped. Okay. So that means that this side here is now sine of theta, while this side is cosine of theta. And by comparing the two similar triangles, we can find a value for cosecant and cotangent. So let's do that. So cosecant theta, that's the hypotenuse of the large triangle, okay, over, maybe let's label this again. This is O. Let's call this, I'm going to use different letters like C and D, okay. So notice OC is 1 because it's the unit circle still, right? This is still the unit circle. Nothing has changed, okay. So that means OC is equal to 1, okay. So cosecant of theta, which is the hypotenuse of the large triangle, over the base of that triangle, which is OC, okay, is in the same ratio as the hypotenuse of the smaller triangle, okay, over its base, which is sine of theta. So in other words, since this expression here is 1, this means that cosecant of theta is 1 over sine theta. And if we look at cotangent of theta, now that's the height of the larger triangle over OC again, maybe over the base. That's in the same ratio as, let's see, the height of the smaller triangle, which is cosine, over the base of that smaller triangle, sine. So we see that cotangent, so again, because OC is 1, cotangent of theta is just cosine over sine. That is, by the way, the same as 1 over sine over cosine. And 1 over sine over cosine is tangent. So cotangent is 1 over tangent. So to summarize everything, what do we have? We have sine, cosine. We've got secant of theta. That's 1 over cosine. We've got cosecant of theta. That's 1 over sine. We've got tangent, which is sine over cos. We've got cotangent. So I wrote cotangent. Sometimes we just write cot, or okay, so both are acceptable. Cotangent of theta is cosine over sine, and we can also say that cotangent is 1 over tangent. Here you go. You've got them all. So from sine and cosine, we can create 4 more trig functions, which are secant, cosecant, tangent, and cotangent, and they all have a geometric meaning with respect to the unit circle. When you and you can find them back by recreating those 2 triangles. Now, this is not something you want to do all the time, so it's preferable to remember those relationships that I framed, so that you don't have to reinvent the wheel all the time. But I wanted to show you where this is something I was never shown, by the way, when I was in Sec 5, like where those where the terminology of sine, cosine, tangent, cosecant, secant comes from. I was basically just told these identities that I framed, but they all have like a geometric relationship with respect to the unit circle.